Hello, my name is Haocong. I will be presenting CLR-DRAM, a low-cost DRAM architecture that enables a dynamic capacity-latency trade-off. This work is motivated by the fact that workloads and systems have varying memory capacity and latency demands. However, commodity DRAM as the prevalent technology for main memory makes a static capacity-latency trade-off at design time. As a result, commodity DRAM could not adapt to changes in the workload and system's memory capacity and latency demands. Our goal is to enable a dynamic capacity-latency trade-off in DRAM at a fine granularity, that is, a single DRAM row to meet the changing capacity and latency demands of the workloads. To this end, we propose CLR-DRAM, which stands for Capacity-Latency-Reconfigurable DRAM. CLR-DRAM is capable of dynamically reconfiguring a single DRAM row to operate in either a max capacity mode with high storage density or a high performance mode that can operate with low access latency and low DRAM refresh overhead. The key mechanism of CLR-DRAM consists of two techniques. First, we can couple two adjacent DRAM cells in a row and their two sense amplifiers to operate as a high-performance logical cell. Second, we can dynamically turn on and off such coupling to switch between the two modes. Our SPI simulation shows that a high-performance mode row in CLR-DRAM significantly reduces four major DRAM cell access timing parameters. Our system-level evaluation shows that mapping pages to high-performance rows in CLR-DRAM improves average system performance and saves DRAM energy. We hope that future work explores CLR-DRAM to develop more flexible systems that can adapt to the diverse and dynamically changing DRAM capacity and latency demands of the workloads. Here's the outline of the talk. There's a fundamental trade-off between storage capacity and access latency in DRAM. Commodity DRAM overwhelmingly favors storage capacity at the expense of long access latency. Modern workloads have different main memory capacity and latency demands. Existing systems miss the opportunities to improve performance by adapting to the changes in memory capacity and latency demands. The memory capacity of a system is usually over-provisioned, while many modern workloads tend to underutilize the system's memory capacity. However, commodity DRAM as the prevalent technology for main memory makes a static capacity-latency trade-off at design time. Once manufactured, they are either capacity optimized at the cost of long latency or latency optimized at the cost of small storage capacity. Even some state-of-the-art heterogeneous DRAM architectures employ only a fixed size and small low latency region, which does not always provide the best possible operating point within the DRAM capacity latency trade-off spectrum for other workloads. As a result, commodity DRAM could not adapt flexibly to the changes in the system's memory capacity and latency demands. Therefore, our goal is to enable a dynamic DRAM capacity latency trade-off at a fine granularity, that is, a single DRAM row, as shown pictorially in this figure. Next, I will briefly introduce how DRAM works. A DRAM chip contains multiple independent DRAM banks, each consisting of multiple subarrays of DRAM cells. A DRAM cell stores one bit of data using electric charge level. A typical density-optimized subarray architecture is shown on the right. To access data stored in the DRAM cells, the memory controller issues an activate command to activate a row of DRAM cells. The electric charge in the cells are then sensed and read by sense amplifiers placed on both sides of the subarray through bit lines. This kind of architecture is called open bitline architecture. The sense amplifier operates in a differential manner. It reads data stored in the cell by sensing and amplifying the voltage difference across a pair of bit lines caused by the sharing of charge between a DRAM cell and a bit line when a row is activated. During activation, another bit line in a neighboring subarray is also involved to serve as the reference of the sense amplifier. Here, we show the procedure of accessing a fully charged DRAM cell. The x-axis is time, and the y-axis is voltage levels in the cell and the bit lines. The activate command let the DRAM cell share its charge with a bit line. This creates a voltage difference across the bit line pair. When the difference is large enough, the sense amplifier starts to amplify this difference and enters the charge restoration process. During charge restoration, when the voltage difference is large enough, we can safely issue a read or write command to the DRAM row. The latency between an activate command and the earliest possible read or write command is called TRCD. At the same time, the charge restoration process continues to restore the charge level back to the cell. The latency of fully restoring a DRAM cell is called TRES. After TRES, the row can be safely closed by pre-charging it. The memory controller issues a pre-charge command which takes TRP amount of time to close the row. Due to charge leakage, DRAM cells have to be periodically refreshed to ensure data integrity. Now, I will introduce our new idea, CLR-DRAM, Capacity-Latency-Reconfigurable DRAM. CLR-DRAM is a low-cost DRAM architecture that enables a single DRAM row to dynamically switch between either max capacity or high-performance mode. The key idea of CLR-DRAM is to enable dynamic configurability of the connections between DRAM cells and sense amplifiers in the density-optimized open bitline architecture, which is shown on the left. To do so, CLR-DRAM, which is shown on the right, has two types of small isolation transistors, called Type 1 and Type 2 bitline mode select transistors, to enhance the connectivity between DRAM cells and sense amplifiers. For a row to operate in max capacity mode, CLR-DRAM enables Type 1 and disables Type 2 bitline mode select transistors to mimic exactly the same cell to sense amplifier connections as in the open bitline architecture. Doing so enables every single DRAM cell and its sense amplifier in a max capacity mode row to operate individually. This achieves the same storage capacity as a row in the conventional density-optimized open bitline architecture. For a row to operate in the high-performance mode, CLR-DRAM enables both types of bitline mode select transistors to enable two kinds of coupled operations simultaneously. First, two adjacent DRAM cells in a row are coupled to operate as a single logical cell, because they are connected to both ports of the same sense amplifier. Second, two sense amplifiers, which originally served the two adjacent cells individually, are now coupled to operate as a single logical sense amplifier, because the logical cell is connected to both the two sense amplifiers. A high-performance mode row in CLR-DRAM has reduced access latency and refresh overhead via these coupled cell and sense amplifier operations. Next, I will explain how could the coupled operations in high-performance mode rows reduce access latency and refresh overhead. I will start by describing what coupling two cells and two sense amplifiers enables. A logical cell always stores opposite charge levels in the two coupled cells to represent the same bit of data. This is because the sense amplifier always drives the two bit lines that each of the coupled cell is connected to respectively into complementary voltage levels. This property of a logical cell enables three benefits to the operation of a high-performance mode row in CLR-DRAM. First, it reduces the latency of charge sharing. Second, it enables the early termination of charge restoration. Third, it enables retaining data stored in the logical cell for a longer period of time. A logical sense amplifier operates faster by having two sense amplifiers driving the same logical cell. This also enables three benefits: the reduction in the latency of charge restoration, pre-charge, and refresh. Now, let me explain how operating with a logical cell and a logical sense amplifier reduces DRAM access latency. As a recap, the coupled operations of two cells and two sense amplifiers reduces DRAM latency in three ways. These three ways of latency reduction altogether reduce the activation, restoration, and pre-charge latencies of a high-performance mode row in CLR-DRAM. The opposite charge levels stored in the logical cell reduces the charge sharing latency by driving both bit lines of a sense amplifier into opposite directions during charge sharing. It reduces charge sharing latency because the voltage difference across the two bit lines reaches the threshold voltage required by the differential operation of a sense amplifier earlier than the baseline case where only one DRAM cell is involved during charge sharing. The opposite charge levels stored in the logical cell also enables a high-performance mode row in CLR-DRAM to terminate its charge restoration early. We make two observations about charge restoration. First, the charge restoration process has a long tail latency. Our motivational SPICE simulation shows that it takes about half of the charge restoration time to fully restore the last 25% of the charge in a charged cell. This means that if we terminate the charge restoration process earlier, the charge level restored in the cell does not degrade significantly. Second, a discharged cell restores much faster than a charged one. This is because the restoration current of a charging cell is limited more than that of a discharging cell. In other words, if we terminate the charge restoration process of a logical cell earlier, we can still have the discharged cell fully restored. Leveraging these two observations, we reduce TRES by terminating the charge restoration process early. Our SPICE simulation shows that TRES could be significantly reduced with only a marginal negative impact on TRCD due to the reduced charge level in the cell prior to deactivation. The logical sense amplifiers reduces the charge restoration latency simply by having two physical sense amplifiers driving the same logical cell from both ends of the bit lines. This largely offsets the long latency caused by long bit lines in the density-optimized open bitline architecture. The pre-charge latency is also reduced because two pre-charge units, which are associated with the sense amplifiers, are also coupled to pre-charge the bit lines together. As a result, by having coupled operation of two DRAM cells as a single logical cell and two coupled sense amplifiers operating as a single logical sense amplifier, CLR-DRAM reduces deactivation, restoration, and pre-charge latencies. Now, let me explain how CLR-DRAM mitigates DRAM refresh overhead in high-performance mode. CLR-DRAM reduces DRAM refresh overhead of high-performance mode rows in two different ways. First, it reduces the latency of a refresh operation. This is because since refreshing a row is essentially restoring charge level back to the cells and then performing pre-charge to close the row. The activation, restoration, and pre-charge latency reductions also apply to reduce the latency of refreshing a DRAM row. Second, since a logical cell contains two physical DRAM cells, it has a larger effective capacitance to tolerate more charge leakage. Therefore, less refresh operation is needed for high-performance mode rows. We conclude that CLR-DRAM could reduce both the refresh latency and the refresh rate for rows operating in high-performance mode. Now, let me move on to the evaluation. We evaluate the latency impact of CLR-DRAM using SPICE simulation. We model a CLR-DRAM subarray based on previously published technology parameters. We scaled these parameters to match with recent technology nodes. We will make our model available freely soon. First, we show the four major DRAM access latencies of a max capacity mode row. We make two observations. First, the pre-charge latency is significantly reduced even for max capacity mode row because two pre-charge units can also be used to pre-charge the bit lines together when closing a max capacity mode row. Second, the bitline mode select transistors slightly increase the restoration latency and write recovery latency and reduce the activation latency of a max capacity mode row. For a high performance mode row, we reduce all the four access latencies of DRAM significantly, ranging from 35.2% to 64.2%. We make two observations about the early termination of charge restoration. First, applying early termination of charge restoration reduces the charge restoration latency even further, with only a marginal increase in activation latency due to the reduced charge level prior to the activation. Second, the early termination of charge restoration also enables the reduction of the write recovery latency, which is not reduced without such early termination because only one write driver is involved to write to the two coupled cells. We conclude that CLR-DRAM significantly reduces DRAM latency. We evaluate the system-level performance and DRAM energy impact of CLR-DRAM. We use RAMulator, a cycle-level DRAM simulator, to evaluate the system-level performance of CLR-DRAM. We analyzed 41 real single-core workloads from benchmark suites, 30 synthetic random and stream access workloads, and 19 randomly chosen multi-programmed 4-core workloads. We model 5 configurations of CLR-DRAM. Each configures a different portion of all the DRAM rows to high-performance mode. For each configuration, we also map the same portion of the most accessed pages of the workloads to high-performance mode rows. I will start with the performance impact of CLR-DRAM. For real single-core workloads, CLR-DRAM provide an average speedup of 12.4% when all pages are mapped to high-performance mode rows. For the 19 multi-core workloads, mapping all pages to high-performance mode rows could provide an average of 18.6% speedup. We observed that, in all cases, the performance improvement increases when we increase the number of pages that are mapped to high-performance mode rows. For the configuration that all rows are configured to operate in max capacity mode, CLR-DRAM still achieves a small but positive performance impact, mainly because of the significantly reduced pre-charge latency of coupling two pre-charge units. We conclude that CLR-DRAM improves system performance for both single-core and multi-core workloads. Next, we evaluate the DRAM energy consumption of CLR-DRAM. Mapping pages to high-performance mode rows yield an average of 19.7% DRAM energy savings for single-core workloads and 29.7% for multi-core workloads. We conclude that CLR-DRAM saves DRAM energy. High-performance mode rows in CLR-DRAM could mitigate the DRAM refresh overhead by both reducing the refresh latency and the refresh rate. First, we observed that only reducing the refresh latency in CLR-DRAM already saves DRAM refresh energy by 66.1% on average for multi-core workloads. If the refresh rate is reduced by 3x, which our SPICE simulation showed is possible, CLR-DRAM could save DRAM refresh energy by 87.1%. Doing so still achieves an average speedup of 17.8% for multi-core workloads. We conclude that CLR-DRAM significantly reduces DRAM refresh energy. We conservatively estimate CLR-DRAM to have a modest DRAM chip area overhead of 3.2%. Configuring rows to high-performance mode incurs memory capacity overhead. However, due to the flexible reconfigurability of CLR-DRAM, the user is free to find and dynamically determine a favorable operating point in the DRAM capacity-latency trade-off spectrum. We have more detailed overhead discussions in our paper. We conclude that CLR-DRAM is a low-cost DRAM architecture. We also have a more detailed sensitivity analysis on the trade-off between reducing refresh rate and the increased activation and restoration latencies, as well as at the system-level impact of such trade-off in our paper. Our paper also includes some design details that make CLR-DRAM work efficiently. Now, let me conclude my talk. We propose CLR-DRAM, capacity-latency-reconfigurable DRAM. CLR-DRAM is a new DRAM architecture that enables dynamic fine-grained reconfigurability between high capacity and low latency operation. CLR-DRAM can dynamically reconfigure every single DRAM row to operate in either a max capacity mode that maintains almost the same storage density as the baseline density optimized open baseline architecture by letting each DRAM cell operate separately, or a high performance mode that provides low access latency and low DRAM refresh overhead by coupling every two adjacent DRAM cells in a row and their sense amplifiers. Our evaluations show that CLR-DRAM significantly reduces 4 key DRAM timing parameters, improves system performance, and saves DRAM energy. We hope that future work explores CLR-DRAM to develop more flexible systems that can adapt to the diverse and dynamically changing DRAM capacity and latency demands of their workloads. Thank you for listening to my talk. For many more details, I invite you to read our ISCA 2020 paper.